Boom.
Good morning, ladies and gentlemen. Let's make sense of what happened yesterday.
It's always nice when things make sense.
Yeah. A resonator reflects waves back and forth at a particular frequency.
Yeah, we have a resonator right here.
And let me get my paper here. Okay, so here is a resonator. Here's a resonator. Okay.
Yeah.
And what happens is when I hit the pipe, I'm sending
Ma, ma.
Okay, so what's happening here? I'm hitting the pipe and I am sending a pulse, a sound wave down the pipe, right?
Yeah.
And that sound wave is constrained by the pipe.
Yeah,
Yes?
it wants to spread out like a bubble,
But it can't.
can't.
Okay, and what happens at the end here? Well, some of it's going to spread out like a bubble,
Yep.
right? And then some of it is going to be reflected and it's going to go back inside the pipe.
Anytime a wave encounters a boundary, some of it is transmitted and some of it is reflected.
Yeah, and so what we have is some of the sound is transmitted and then some is reflected back and forth at a specific frequency.
Yeah, so it's got an open end, and then your hand closes it, and so it goes back and forth.
Okay, and every time some escapes, and then somebody gets trapped in here.
Yeah.
Okay, so that is a resonator, and that's what's happening. We've got waves being reflected back and forth at a particular frequency inside of the pipe, our closed resonator.
Yeah.
A closed pipe resonator reflects with inversion from one end and without from the other. Okay.
What the heck does that mean?
359.
Well, here you've got a compression that goes down and a compression that leaves up. So what you have is a compression down, and you get constructive interference right here. Here at an open end, you have a compression that's going down. When it reaches the end, you have a stretch. You got a squeeze coming in and a stretch goes out because it lowers pressure as this goes out. So here you have a squeeze and a stretch, and you get destructive interference. So constructive interference from one end because you've got no inversion, and then you get inversion here at the other end. Remember, inversion, you've got a wave on one side and it comes back on the other side.
And Boykin, where is that happening at in the pipe? So I smack this.
Okay, so in terms of pressure, there's no inversion here. There is inversion here. So you get, so that's what it means. It's, and what's going on here? Well, here when you get a reflection, you get a high pressure in, high pressure out. Here when you get a reflection, you get high pressure in, low pressure back.
Okay, so that's what we got going on with our closed pipe resonator. Now, a closed pipe resonator has different parts of a standing wave at either end.
Since you have different conditions, one end's closed, one end's open, you get different parts of a standing wave at either end.
And so for all closed pipe resonators, they're gonna always be they're gonna follow a certain formula, I guess you can say.
Yeah.
So let's take a look. One end is gonna have a node and one end is gonna have an antinode, always. And I think we're gonna go ahead and talk about our drawing over here now.
Yeah.
Okay. All right, so here we have one bump is one wavelength, right? Half a wavelength,
half a
right?
wavelength.
So we've got a full. So if we've got two bumps, we've got one wavelength.
Full wavelength, yeah.
A full wavelength. We've got nodes here. We've got antinodes up here.
So two bumps is a full length wave, but it takes.
So it says a closed pipe resonator has different parts of a standing wave at either end. It has a node at one end, so here's a node, and an antinode at another end. So that's right there, right?
Yep.
Okay, so if my wavelength is from here to here, let's see, 1, 2, 3, 4, that's going to be 1/4 of a wavelength,
Yeah,
isn't
how
it?
much of a wave is between a node and an antinode? And it's 1/4 of a wavelength.
Okay, cool. So when we're talking about a closed pipe resonator, okay, there will always be a node at one point and an antinode at the other.
That's right.
Oh, whoa.
Gee,
What
there's the
the-
whole lesson, boys and girls.
I think we're right here. Okay, I'm going to go.
Yep.
Is it this one?
The
We
next-
just finished
yep.
that one. Okay. All right. So here is a picture, right? So if this whole thing is, if this little chunk right here is my pipe, okay, that's my closed pipe right here.
Yeah.
Now, how much of a wave do I have in there? I have one wavelength.
1/4 of a wave.
1/4. Excuse me.
Inside.
1/4 of a wavelength inside. So.
How long is the whole wave?
How long is the whole one? Oh, it'd be one. It'd be this times 1, 2, 3, 4.
Yep.
Right?
If you got
Okay.
1/4 of a wave, how long is the full wave? 4 times as long. Does that make sense?
It makes sense, right? Okay, and all closed pipe resonators are going to do this. Ignore this.
Yeah, I'm keeping it out of the picture.
We don't care about that, okay? All right, so there is a 1/4 of a wavelength between a node and an antinode. Yes. There is a 1/4 of a wavelength between here, a node and an antinode. And that is what we have.
So slap the pipe here
Okay.
and make the sound. So you got 1/4 of a wave. How long is the whole wave?
Well, it's going to be this times 4, whatever this length is,
Yeah.
times 4. 1, 2, 3, 4. Okay?
That's right.
All right, so this frequency, I couldn't hear myself there. This frequency depends on the length of the pipe and the speed of sound.
Yeah, we've got 2 pipes here. We've got a shorter one and a longer one. And hit them both.
Oh, yeah. So here we go.
No,
Okay, so this one has a higher pitch, right?
no. Yeah, so the lower pitch has a longer wavelength. So if the speed of sound is 343 meters per second, the relationship between the frequency and the wavelength multiplied together gives us that velocity.
Oh, okay. And you know what? So that's this equation right here, right, Blake?
Yes, it
This
is.
one? Okay, so we're gonna be taking a look at this relationship right here. Okay. Now, okay, so challenge. Find the frequency of your closed pipe resonator. Okay, which one do you guys want to do?
6 of one, half does the other.
We'll do this one. Okay. All right. So, well, first of all, let's write the equation on the board, like we just said. I'm gonna keep this up here. I feel like it's a good visual. I can't.
Yeah, so we solved that for frequency. Frequency is what we want to find.
We know the speed of sound is always 343.
Yeah.
That's what we're gonna go with, and we want to solve for frequency. So frequency is gonna equal the velocity over the wavelength. I just divide by wavelength.
Yeah, so let's measure the length of the pipe.
Okay, so the length of the pipe is going to be. Okay, so it's gonna be. You want to call it 35?
35.35 meters.
Okay, so the length is 0.35 meters. Okay, so I should just be able to do the frequency times the velocity, which we said is 343 meters per second. Okay, divided by the wavelength, which is going to be 0.35, right?
Yeah.
Okay, so let's see. So 343 divided by 0.35, and I get 980.
980 hertz. Cycles per second.
Okay, let's check ourselves.
Bring the pipe.
Yeah. Okay. Oh, and my mouse. I always forget my mouse. All right. So we said 980.
980. And use it, yeah.
980.
So
Okay.
slap the pipe first. No, no, no.
Ooh.
No, that's not it.
Oh, that's not it for sure.
No.
What did we do wrong?
Well, what did we do?
Well, we said that okay, so this one is fixed. We must have done something wrong with our wavelength here. We said that the length of our wave is going to be 0.35, right?
But
From
what,
here to here.
inside a closed pipe resonator, we only have 1/4 of a wave.
Okay, so
So we used the wrong
we
wavelength.
use this. So we need to multiply that 0.35 times 4 in order to get this number right here.
Yeah.
So let's do 0.35 times 4. 0.35 times 4, and I get 1.4.
1.4 meters.
Okay, so 1.4, that's going to be our wavelength from here to there. From our
You guys
customer.
understand the mistake we made and how we're fixing it?
Yeah, I understand.
Yeah.
Okay, so, I didn't do my math, sorry. So 343 divided by 1.4, and I get 245.
245 cycles per second.
That's a big difference. Okay, 245 cycles per second. Let's check it out. Okay, so 245.
Slap that sucker. No, 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 no. Nailed it.
There we go. Okay. All right. So, ooh, I just realized Boykin for homework. I can give him this one. Okay. Come on. Maybe. We'll see.
Yeah, I like that.
Okay. So, the length of a closed pipe has 1/4 of a standing wave in it. how do we know? What did we just do?
Yep, we proved it.
Yeah, so we know the velocity and we measured the length of our resonator,
Yeah.
our resonating pipe. And at first we did, 0.35 meters.
Use
and
the
we
length
said,
of the pipe as a
we
wavelength.
said the whole wavelength is this long.
That was wrong.
And when we checked with our tone generator, no. So we know, and then from there we said, okay, there's a quarter of a wavelength in here. Okay, so
How long is the whole wave?
So the whole wavelength is gonna be 4 times this thing. So, and we used our tone generator to check our work there. Okay, so, and again, in case you aren't with me still, so in our closed pipe, this being our pipe right here, we have a quarter of a wavelength. We've got 1, 2, 3, 4. We have to multiply it by 4 to get the total length.
So 1/4 of the wave's in the pipe, 3/4 of the wave is
There you go.
outside.
Boom. Fractions. All right, so the loudest sound from a closed pipe resonator is a quarter wavelength.
Yep.
And we just call this a fundamental frequency. So this is the fundamental frequency.
Yep.
Good morning, Cougars, and happy Friday.
I just realized that this is Emerald.
Who is it?
Emerald, one of our basketball players.
Oh, yeah.
Anyways, she's just so peppy.
Ah.
Okay.
And to the republic for which it stands,
Should we keep
one
going?
nation,
I don't know.
Well, we could go here.
here.
A closed pipe resonator has more than one wave standing in it. Okay. Oh, okay. So if this is the pipe, we can have more than one standing wave in it. But notice, check this out, how we have a node, antinode, node, antinode, node, antinode.
So each bump, this is a quarter of a wave.
Mm-hmm.
This is 1/4, 2/4, 3/4 of a wave.
Mm.
This is a bunch more. Actually, 1/4, 3/4, 5/4. They're in
Yes.
odd multiples.
Okay, so here is another visual of that. And, we call these, the harmonics or the fundamental frequencies. This is the fundamental frequency.
That's the loudest sound that you'd hear.
Yeah, and it doesn't matter how many more wavelengths you squeeze into there,
Yeah.
it's still just going to make that sound.
And here's the deal about this. The harmonics that are present that are not as loud as the fundamental give quality to the sound. And we'll talk more about the quality of sound going forward.
So these are called harmonics and are all shorter wavelength than the fundamental frequency. Okay,
Yeah.
and you can see that, right? So you can see that this wavelength is going to be longer, and then you can see there's more waves being squished in here. The wavelengths are being squished. The wavelengths are getting smaller.
The
and that's gonna
frequencies
affect the
get
frequency.
higher.
I think before I said that the more wavelengths you fit in here, it's not going to affect the sound. It does affect the sound.
It does,
right?
yeah.
And so.
But the loudest one you hear is the.
Is that first one? These are called harmonics, and they're all shorter wavelength than the fundamental. Okay. Each wave has a node at one end and an antinode at the other, and you can see that again. Node at one end, boom, boom, boom. Antinode at the other. That is that commonality that we see for
Yep.
all of them. Okay. For homework for this. Question: what fraction of a standing wave is in a closed pipe resonator?
Yeah.
Okay. And 2, describe how to find the wavelength of this standing wave. Now let's go ahead and give you. So I want you to use words to describe how to do it, and then for the very last part of this homework assignment, let's add this in there.
How long is it?
This is. We'll call it 46.46 meters.
So for this pipe, find the length of the standing wave, and then find the frequency of the sound. You know,
Now, Boykin, we want to wait for this for.
yeah, this we'll do later.
We'll do the open pipe stuff later.
Yeah,
Okay.
let's just stop here.